Hi there, in this video we're going to look at parallel lines, perpendicular lines and lines that run parallel to the axes. Okay, so one that runs along here parallel to the x-axis and ones that run up and down parallel to the y-axis. So let's first of all look at lines that are parallel to the x-axis. Now, one thing that all the points of a line that's parallel to the x-axis have in common is that their heights are always the same. Okay, so for example, a line that runs along here will all have height 1. Okay, so they'll have a y value equal to 1. So let's try putting in y equals 1 and see whether we actually get that line. So we put in y equals 1 and there you go, we've got a line that runs parallel to the x-axis. Now we can change the position of this line here just by changing this number, so we could make it 2 or 3 or 4, or we could go -1, 2, 3, 4, 5. So by changing this number here we just change the height of this line. Okay, so that means that we can write a line that's parallel to the x-axis can be just be written as y equals c. Okay, where c is just a constant, it's just a number. Okay, now you can see as well, if I click on this here, you can see that if I put this back to 1, then if I click on that pointer, you can see that the x value changes. Okay, you see the x value changing all the way along, but the y value always remains at 1. Okay, even back this way, the x value changes, but the y value stays at 1. Now, let's say we want to look at a line that's parallel to this y-axis. Now, if we had the line and it just runs, say, down like this, then the one thing that all the points have in common is that all of the x values are going to be equal. Okay, so let's say we want a line where the x values are equal to 1. So we could just say that, well, let's say all the x values equal 1. So there we have a line there where all the x values are equal to 1. And you can see that again, if you click on that, you can see the x value remains at 1 as all the y values change. Okay, so that's a equation of that line is equation x equals some constant c. Okay, so that's will give you a line that will be parallel to the y-axis, and you can see that as we move that up and down. You see, there you go, and as that value changes. Okay, now we've already seen before that if we were looking at lines that are parallel to one another, that they would have the same gradient. So for example, I have y equals 2x, okay, then in order to draw a line parallel to that, I could just add on a value of 1, 2, 3, 4, 5, or -1, 2, 3, 4, 5, and I'll have another line that is parallel to this line. Okay, so let's just do that now. If I went +1, okay, then we've got a line that would be parallel, so I'll put in the original line actually, y equals 2x. Okay, so this is the original line here, and you can see that line there is lying parallel. Okay, because the value here of the gradient is the same. Okay, so we could put in a number here for this constant. Okay, so we could just call it c. Okay, and then we could go and get the slider, and we can just say, well, all those lines, if you see I slide it up and down, all those lines are parallel. You know it's parallel because watch what happens when I sit on it. Look, it's exactly the same line, you see, and if I move it off, all those lines are parallel. So they're parallel if the gradient is the same. So we kind of seen that in the previous couple of videos. Now, another interesting thing that we're going to look at is that what happens, how do we find a line that runs perpendicular? Now, perpendicular means at 90 degrees. So if I was to draw out a simple line, y equals x, then if we wanted to have a line that is at 90 degrees to that, well, a line would run up and down that way, okay? And so if we were to, we know that in order to draw that, at this point here we come along one and up one, okay? Now the one that runs parallel, perpendicular, would have to come along minus one and up one, okay? So if we were to note that the one that runs down this way would be the same line as this, okay, but it would just be a negative gradient, okay? So the gradient there would be negative as opposed to the gradient here being positive. So let's just write in what we think it might be. So we're saying that y would equal, well, the gradient would be negative, so it would be negative x, and there we go. You see you've got a line there that is running perpendicular to this line, so it runs at 90 degrees, so that's 90 degrees there. All of these are 90 degrees, okay? Now what if I then went and said, what about the line, well, 2x, I want to find a line that runs perpendicular to the line y equals 2x. Well, this one doesn't run perpendicular, that is not a 90 degree angle, okay? So we know that if we went along 1 and up 2, okay, in order to get a line perpendicular, instead of going along 1 and up 2, we would go along minus 2 and up 1, okay? So that would mean that in order to get this line here, that we would have to change the gradient, okay? So let's get rid of that one there because that's I'm not using it. So we would have to change the gradient so that the line there was a value which is along minus 2 and up 1, so the gradient that there would be minus a half, okay, because it's in the minus direction for gradient, and we would go along 2 and down 1, okay, so the gradient would be 1 upon 2. So let's just try that. So we'll probably put in y equals minus 1 divided by 2x, and there you go, you've got a line that is running perpendicular to this line. And if we had a line that was, say, 3x, that would be minus 1 upon 3, okay? Now the thing to note is that whenever you multiply these two together, so if I multiply 3 by minus 1 upon 3, I get the value of minus 1, okay? So if I was to make that say 7, okay, and I wanted to find the gradient that was of the line that was perpendicular to that, I would have to make that minus 1 upon 7, okay? So then if you multiply these two gradients, you're going to have 7 times minus 1 upon 7, which is minus 1, okay? So we've got a way there to tell if two lines are perpendicular, because whenever you multiply the gradients, when you multiply the two gradients together, if you get minus 1, then the lines are perpendicular. Now you can see this as well. That's just us having a look at it and thinking, well, that looks like that might be the case. So let's have a wee look and see if we can kind of prove it here using the tool we've got. So if I take a simple line y equals x, okay, then we know that we've got the gradient of, it's like equivalent to saying 1x. So let's look at more general. Let's say we have a line and we say the gradient y equals m1x, okay, so that means that we've got a line there that's gradient is equal to m1, so that in instance there the first gradient is just m equals 1, say along 1 up 1, and you can see you can change that round about like this here, okay. So let's get that back up to 1. Now if what we said is right, we said that if you multiply both the gradients m1 and say another gradient m2, then if the lines are going to be sitting perpendicular, then m1 times m2 would be equal minus 1. Or you could say that a new gradient, say m2, would equal 1 or equal minus 1 divided by m1. Now if you don't quite get this, I'm going to draw it out later and we'll just derive it on the pen and bit of paper. Okay, so we've got a new gradient there, m2. Right, now what we'll do is we'll draw out another line. We'll call it y equals m2 x. Okay, so it's looking good already, because what we've got is we've got a line y equals m1x. Well, this term m1 is just 1. Okay, so the gradient is just 1. And then we've defined another gradient. We'll call this new gradient m2, and we'll make it equal to minus 1 upon m1. So in this instance here it would be minus 1 upon 1, which would just be minus 1. Okay, so then we drew out this new line here with this new gradient. It would be y equals minus 1x, which is just that line there. Okay, now the proof for here to see if it's actually going to work is that whenever I move this here to different values, okay, so as this line here moves round about, this line here should move round about as well, but it should always maintain an angle of 90 degrees, because that's what we've made it do that there by making this little value of the new gradient m2 equal minus 1 upon m1. So let's look and see if that happens, and there you go. Look, so there's a kind of little geometric proof that this does actually work. Okay, and if you've got access to this Desmos tool, so go and give it a wee go yourself. Okay, so that's a kind of little proof there that the gradients, when you multiply two together, you get a value of minus 1. So now let's go in and we could have a wee look at it in pen and paper. So I think I've got it set up here somewhere. Yep, okay, that's us there. So if we were going to do it in pen and paper, what we would be able to say is that if we took some point, okay, so let's draw a wee axis there like that. Okay, so there's our axis. I'll get rid of that wee point there because it's just annoying me. There you go. So draw that to this axis. Now, if I picked a point there, okay, and we call that point A, and it's got the coordinates x1, comma y1. So we come along x1 and we got a value of y1. Okay, so that gives us this little line there. Then if we were to take this point and we move it round 90 degrees, okay, so then it comes up and it comes up over there. And what's going to happen is that this point here, we call that point B, okay, that point B is going to go to the point, now it will be minus y1, comma x1, okay, if that's sitting at 90 degrees. Now you can get in there and check it out in the graphical calculator yourself if you don't believe that. Okay, so now if we were to then say, well, the gradient of this line here, this, we'll call it OA, okay, so that's the gradient from the origin there to that point A. It's just going to be equal to, well, it'll be y1 minus 0 upon x1 minus 0. Now, if we were to look at the gradient of the line from MO to B, the gradient of this line here, then what you're going to get is, again, these have been swapped round about, so what you're going to end up with is you're going to have, for the top line, you're going to, instead of having your value of y1, okay, your y1 is going to be swapped and it's going to be called now x1. So you're going to have x1 minus 0, and the same again, the x value is going to be swapped round about. It's now called minus y1. That's minus y1 minus 0, which equals minus x1 upon y1. Okay, so that means that the gradients, when you multiply them together, that's MOA times MOB, is going to equal y1 upon x1 times minus x1 upon y1, which is going to equal, well, that cancels out, move it up. That one there cancels out with that one there. Okay, and pull this down a wee bit. And so that cancels with that, and you end up with minus x1 upon x1, which just equals minus 1. Okay, so that's a little proof that when you multiply, if two lines are perpendicular, if you multiply the gradients together, you get a value of minus 1. Okay, so thanks, that's all for this one, and there are a couple of videos on straight lines, and then we'll get in and we'll just get through some exam questions. Okay, goodbye.